My name is Idan Revivo. With me, we have Asaf Eitani, and we are security researchers at Aqua Security research team, where we're focusing on new and emerging threats and vulnerabilities in the cloud-native space. Today, we are going to talk about rootkits in Linux environments, specifically kernel rootkits and user space rootkits. We're going to talk about eBPF. We're going to talk about why eBPF is the preferred technology for us to detect real-time threats. And we're going to start things off with an intro. We'll talk a little bit about the playground, what are all the pieces that we'll be going to talk about. We're going to talk about why eBPF is the preferred technology. We'll introduce Tracy, which is our open source. This is where we implemented all the things that we're going to show you today. So everything you're going to see is open source. You can see the code. You can just go ahead and play with it. And then we're going to go and look at each one of the rootkits that we're going to talk about, and we're going to talk about their attack flows. We're going to break them apart, and then talk about how eBPF helps us to detect those things. But first, a quick intro to our playground. Asaf.
Thank you. OK, so let's first look at what we're talking about. What is the playground that we're playing in? And this is the Linux server. We're mostly doing research on cloud security, and most of the cloud is Linux. And this is an abstraction of how the Linux server looks like. So first, we have our user space, which is what we know as the interface of the server. So web application, databases, and stuff like that are in the user space. And we have the kernel space. The kernel space is where the operation system resides, starting from file system all the way to memory access and privileges. The intermediate between the two is syscalls. Syscalls are sort of an API between the user space to the kernel space to allow a user to interact with the operation system. For example, create a file on the file system or read a file, stuff like that. OK, so now that we've seen what the server looks like, we want to monitor what happens there. And we're able to do so with a concept named hooking. So what is hooking? Hooking is the action of attaching oneself between two functions, and by that, gaining the execution flow and the execution context to itself. We're able to run our code in the hooking function, as well as know what function called to the second function, and by that know what is going on the machine. So this is hooking, and we have different tracing method or tracing technologies which enables us to use hooking in order to know what's happening on the machine. So before we pick a tracing method, we want to know what we need to consider, what is the criteria. So first of all, we want it to have a low overhead, so it won't affect the performance of the server. We want it to be covered so attackers won't know that they're being monitored. We want it to be hard to evade so attackers can't disrupt our actions or change our monitoring easily. And we want it to have full system visibility to know as much as we can, and we want it to be safe so it won't crash our system, of course. So we gathered a list of tracing methods in Linux, and we found out that the eBPF is the best tracing technology in our opinion. And soon you'll understand why. As you can see, the top two rows are user space tracing methods. And as you can see, we have too much red X's and not enough green V's. It doesn't have the necessary criteria to allow us to do an effective monitoring of the system. Either it has a high overhead or not as hard to evade, as well as not providing full system visibility because it resides on the user space and the kernel space is hidden from it. And then we get to the third row, which is the kernel module, which seems better and was the go-to solution for many years in terms of tracing methods. But as you can see, we have one red X, meaning that the technology is not safe. The meaning of that is that if we have an error or a bug in our kernel module, that could lead to a system crash or even a vulnerability to be exploited by an attacker. And then we get to eBPF. eBPF, as you can see, provides us all the necessary criteria to be an effective monitoring technique. And it's doing that, it's doing that by running kernel code in the kernel inside of a sandbox. So if we have an error or a bug, we won't be affected and the system won't crash. Here you can see an accurate representation of the architecture of eBPF. So basically, we have a loading of a program from the user mode, a BPF bytecode, into the verifier. The verifier is a component that verifies our code. This is one more action that BPF is allowing us to run secure code on the kernel. And it's doing that, it's doing some checks to check if our code can be run securely on the machine. For example, it checks if we are not doing any null pointer reference or stuff like that. Then the program is loaded into the BPF sandbox, and it's using kprobes, uprobe, trace points, and other probes on the system. Those probes are the hooking that we mentioned earlier. This is what allows us to hook onto certain functions in the kernel and in the user space, and allow us to know what's happening on the machine. The bottom part, the maps, is a communication channel between the kernel component and the user component of the eBPF. We'll be talking mostly about those parts, but we're gonna see it in the next slides. Okay, so this is Tracey. Tracey is our open source tool, which is based on eBPF. As I said, it offers increased observability into the system because it uses eBPF to do its tracing. It offers also some neat features that allows us as security researchers to do our job better. For example, artifact capturing allows us to capture any process executed or file being executed, even if it was executed from the memory. And we'll see an example for that in the next slides. And we offer behavioral detection as well. So we built a rule engine on top of our Tracey, and we're writing rules on the events that Tracey is offering. And by that, we are providing a way to detect malicious and suspicious behavior on your machine. You can go to GitHub to see the source code and use it, and leave any comments or ideas if you have some. And now for the next part, on what is a rootkit, I give you Idan.
Thanks. Okay, so we talked about eBPF, why we think this is a really good technology to help us detect threats in real time. We talked about Tracey. Now let's talk about what is a rootkit. Rootkit is basically a piece of malicious code that is in charge of concealing all the malicious artifacts of the attack, which are usually processes, files, network connections, and of course the ability to hide itself. If it's a shared object, then to hide the shared object. If it's a kernel module, if it's an eBPF program, in all those examples, one important piece of the attack is to be able to hide itself. We'll start things off with LD Preload Rootkit, which is the most common, the most basic one, and easy to implement. All you need to do in order to implement an LD Preload Rootkit is just create a shared object, export a symbol that is part of the system library, for example, any function from libc, and then it's going to intercept the request from libc and modify it. So in a normal execution, we can see that a user space application will want to iterate a dir. It wants to see all the files in the disk in a specific folder. It will call read dir, which is implemented in libc. Libc will get the function request, and then it will call the getDen syscall in the kernel, and the kernel is the one that actually does the job. Then we get the response. The response goes back to the user space application, and this is like the normal execution. But when we had LD preload, we're basically loading a shared object into the beginning of the memory process. What will result is when we are calling read dir, we will call the first instance of that exported symbol, which would be, in this example, our rootkit. And it will call, usually, it will call the original reader. It will go with the same process. But now, when the result comes back, response comes back into user space to the user space application, it will modify the request, the response, and will remove all the evidence from the attack. So how you detect this using eBPF? You can just, what we did, this was our approach to this, we created an event that every time a shared object is being loaded into memory, we check all the exported symbols, and if those symbols are correlating with symbols that are part of the attack, we can create an event that's stating this symbol is being loaded into memory, which is not part of the original library. For the first example, we're going to talk about Hidden Wasp. Hidden Wasp is a user space rootkit, which is a part of the Winty group attack group. Some of its capabilities is file, process, and network connection hiding. And it was based on Azazel, which is an open source LD preload rootkit. So they pretty much just took that code, did small modifications, and used that as part of the attack to conceal the malicious artifacts. You can go to this URL if you want to check out the code. So the first demo, everyone sees it okay? So what we're going to do, we're going to start Tracy. We're going to pass it a filter that says, give me a symbol loaded. And then I'm going to specify if read dir, can you see it? Yeah? No? OK, I hope it's going to be OK. We're going to specify if any shared object is loading the read dir symbol, and it's not part of libc, this is what you see all the way there, then give me an alert. So when I called ls, you can see the malware file. It was normally shown by the ls command. But when I loaded LD preload into the ls command, now I don't see the result. And I get an event that says a symbol loaded from this library, which is Hidden Wasp, and this symbol was exported. So this is how we be able to detect that a shared object is actually overriding a system functionality. OK, so that was just the basic example of rootkit. We thought it would be interesting for you because this is a very common technique. We've seen it in many attacks. Now we're going to talk about kernel module rootkits, which is the most popular, and not the most popular, but the most powerful type of rootkit. We investigated around 30 rootkits that we can get our hands off, things that were public, and also things that we saw as part of our threat intelligence. And after analyzing them, we saw a pattern. We see that most rootkits implementations falls into this attack flow. It always starts the same way. There is only two ways to load a module. Then usually they're going to hide itself. They're going to hide the kernel module. They're going to put the hooks there in the system in order to modify the interaction between the kernel or user space. This is the main component of the rootkit, because this is the part that actually helps the rootkit to hide the other malicious component. It will establish communication channel, because usually there is other parts of the attack. It can be on a different machine or in user space, so they need to communicate. And some of the times, the user space part will ask the rootkit to execute command from the kernel or even give him root privileges. So this is the basic attack flow that we saw. And now we're going to go through each one of them and talk about how they operate and how we can detect them with eBPF. OK, so the first one is loading. There is basically two syscalls that help us load a kernel module, finit module and init module. The main difference is finit module gets a file descriptor. It needs a file in order to load the module. And the other one actually grabs a buffer of a kernel module and loads it into the system. So if attacker wants to be really invisible, usually he will fetch the buffer of the kernel module from the internet, use that syscall, and just load it into the kernel without ever touching the disk and leave any forensic evidence. OK, so the first thing we want to do is to be able to detect it. The way we did it is just put a kprobe on doInit module, which those two functions eventually call, and this is how we can detect that the kernel module was loaded into the system. And the next thing we want to do as part of monitoring and collecting forensics is to be able to capture that buffer as soon as it's traveling into the kernel. We can intercept that buffer, and we're going to copy that outside and send it away to analyze for forensics. So for the next couple of demos, I'm going to talk about Diamorphin. Diamorphin is another open source rootkit, which is very, very popular. We've seen it in many attacks. It has the abilities to hook, to hide files and processes. And also a nice cool thing about him is the ability to communicate with him using the kill command. So he hooks the kill command in order to communicate with the signals of the kill. Okay, so now let's see a demo of how we implemented this in eBPF. We start things off. We give it the capture flag, and we say capture module. When we do that, every module that is going to be loaded into the symbol, we're going to intercept that buffer, and we're going to capture that outside. And we have the doInit module just to tell us to be able to detect that the kernel module was loaded. Now we're going to use our loader that fetches a kernel driver from the internet and using the init syscall in order to load the kernel module in a fileless manner. We got the first event that's stating that the kernel module was loaded. Now we can see in the Tracy out directory that we actually capture a kernel module. And if we look at the strings of the ELF kernel module we detected, we do see the strings of Diamorphin. And again, for this example, this was fileless. This was an attack that there is no copy on the disk. And what we did, we intercepted the buffer. OK, so that was the first piece, loading. Now let's talk about how do you hide a kernel module. The way it usually happens, there is a data structure in the kernel, which is a double linked list that contains all the information of all the kernel modules in the system that are currently loaded. And every time we call lsmod, which is a tool that gives us the names of all the modules that are being loaded, it will iterate over this list and will give us the list back to user space. So all attacker needs to do is just detach itself from this double linked list. It's still loaded into the memory, but now if I'll use the lsmod command, I'm not going to get that. And also some security tools that use this double linked list won't be able to say that this module is loaded. So what we did, there is actually 3 data structures in the kernel that holds copies of this type of information. And we created an event that happens periodically. And every time this event occurs, we check in all those 3 data structures. And if we find any discrepancy, it means that someone is trying to hide itself. So here we can see an example. We implemented a new event in Tracy called hidden kernel module. As I said earlier, this is a periodic check. And we can see that we loaded Diamorphin, this time not filelessly. We just loaded it in the normal manner. We see there is no lsmod we tried to grab for the module. We don't see it. Now we unhide it using the kill command. Now it's visible, so we can see it was actually loaded. And if you consider a hidden kernel module event happened, and it tells us that the Diamorphin kernel module was hidden. OK, now those were the first two stages. The next one is hook placement. As I said earlier, it's one of the most, this is the key component of the attack, because this is the actual place in the attack that actually hides the malicious artifacts. We're going to go over several types of hiding. There is many more, but we only had 50 minutes. So we decided to talk about those, but feel free to come after us to talk about more. OK, the first one is system table hooking. Usually when we call the instruction from user space to kernel, which is the syscall instruction, we give it a number. And this number is being translated by the syscall table into a pointer that points into the implemented code of this syscall. So when I'm using the ls binary, and I'm going to call getDance, I'm going to give the syscall instruction the number 78. It will be translated into the pointer, and then the code of the original syscall will be executed. We can see in the browser example, the File Explorer example, we see the file is there. Now, when we hook the syscall table, we load a new kernel module, that's like happened in Diamorphine. But now what we did, we modified the pointer of the getDance command, the getDance syscall, which is now pointing into our own implementation, for the example of Diamorphine. And he will intercept the request coming, and he will decide what data to return. So as you can see now, when Diamorphine is loaded, the file is not being detected. So how we can detect this with eBPF? All of the symbols of the kernel are between those two symbols, the S-text and the E-text. So every time we get a pointer, we can just check if the pointer is between those two symbols. And this is the address of all the kernel implementation of all the symbols of the kernel. What would happen is we will find that the syscall table is pointing outside of the normal kernel implementation, is actually pointing to another module, which will indicate that, that there is a syscall table hooking in place. This is how it looks like in the Diamorphine implementation. We can see it gets the pointers of the original syscalls, is hooking getDance, getDance64, and kill. It saves them for later because he will need to be able to call the original ones to get the real data, and then he replaces them with his own modified version. And this is how it's going to intercept and hide the artifacts coming for files and processes. And you can see in the Tracey example what we did. We created a new event called hooked syscall. So every time Tracey starts, it will iterate over the syscall table list. If there is any syscall that is pointing outside of the kernel, we will give it an alert. We can see in this example, before Diamorphine was loaded, there is nothing, all the symbols are there. Then Diamorphine is loaded, and now we get a second event every time a kernel driver being loaded, and it's stating that those three symbols were overridden. And also we can see that they are pointing into a hidden location. So we try to fetch the data from the linked list, but it's not there. So we are able to say those syscalls is not only overridden, but they are pointing to a hidden location in the kernel. So now, for more strategic places on how you can achieve the same goal, I give you Asaf.
Thank you, Dan. OK, so we see on how we can hook the syscall table. And that's all fun and games, but we want to go deeper into the kernel. So there are methods to detect syscall table hooking. We want to go deeper into the calling function. And we're doing that by performing a file operation hooking. Sequence operation hooking, which we mentioned before, works the same way. So we're going to demonstrate only file operation hooking, but it's basically the same, just it's on different artifacts. So file operation works on file and processes. Sequence operations is on network connections and such. So how does it look like? What is file operations? File operation is a structure inside of the kernel. We specify for a file system what are the actions that are allowed on each file and what functions needs to be executed in order for those files to be, for those actions to perform. So for example, you can see we have the write, we have the read, and we have iterate and iterate shared. Those examples, iterate and iterate shared, are used in order to list a directory. So in this example, we can see what happens backstage in the kernel. So we have an ls command, which calls the getDance syscall, which in turn calls to the file operation pointer, pointing to iterate shared, a function in the kernel, and that goes back into the user space to return the results. What attackers might do is they might change the file operation pointer. And by doing so, they're able to capture the response back into the user space and remove any artifacts from those results. This can happen for both files and processes, as processes in Linux are represented as files. So this is how file operation hooking works. And one of the APTs that use that is Drovorov. Drovorov is a Russian APT used by the GTSSS. also known as APT28. And as you can see, it allows file and process hiding, and the communication channel between its operators and the malware is WebSocket. Also, there is no available sample in the wild, but we do know how it attacks based on an NSA report published about this malware, which specifies that this malware is performing file operation hooking and sequence operation hooking. In the demo we're about to see, we used a POC code by a user named Nisai that implemented this technique on a malware named phide. So I hope that you can see. We're going to try something. Is that going to work? OK. So as you can see, we have our Tracy running with -f e equals do init module just to see that the module was loaded, and the hooked proc fops event, which we added in order to know that this occurred. And below, as you can see, we have our malware running in the background, and we're able to see it. Now, when we are hiding the malware, two events will pop up. Those are the procfops hooked events, as you can see. And they're indicating that phide is hooking the iterate shared function in order to hide artifacts. And as you can see below, when we do ps and grep for malware, we're unable to find it. Then we remove the phide malware and do ps again, and we're seeing the malware. It's still there. We haven't killed it yet. OK. So we've seen so far a loading of kernel module, and now we are able to capture them. We've seen how kernel modules are able to hide themselves. And we've seen two types of hooking, or three types of hooking, including the sequence operation hooking, in order to hide artifacts. The third method is, the next stage is communication channels. And this is really a war of creativity. Threat actors can use any mean in order to communicate with their kernel module, starting from network packets all the way to devices, either new or overridden devices. And as we've seen in the diamorphing example, they can also override syscalls in order to communicate with the malware and give it command. Our next stage is command execution. So this is the final stage that kernel modules are allowing, the kernel rootkit. And when we look at a normal execution, basically it's performed by the execve syscall. The execve syscall, as you can see, calls in turn to security BPRM check, which calls to scheduled process exec. Those two are functions inside the kernel that spawns a new process execution in the user space. And what we found out was that there is another function inside the kernel that does exactly that, which is the call user mod helper function. The cool thing about it, and why we mention it, is because most security tools will hook themselves on the execve syscall to try to find process execution on the system. And by using call user mod helper, you are able, or attackers are able, to spawn new process execution on user space without being monitored and without being detected. So what we did is we placed hooks upon all of those, specifically on the scheduled process exec command, because it's the last one. And now we're able to see if a process execution happened from the user space or from the kernel space. To give an example of how that works, and for example, of an APT or a malware that does that, we have Reptile. Reptile is a kernel module. It's open source. It's used a lot in attacks, mainly by Winty or APT41. And it's able to hide files, processes, and network connection, and also has the ability to give root access to unprivileged processes. We're going to see an example for that. And here we can see first an execve, meaning a normal execution. And below it, we can see the scheduled process exec. And in red, I don't know if you were able to see that because it's a weird color. But we have the invoked from kernel flag, which is 0, meaning this process was spawned from the user space. And then we have below our call user mod helper, which was called by the Reptile malware, the Reptile rootkit. And after it, we can see that it called sketch process exec, which it's invoked from kernel flag is 1, meaning this process execution was performed from the kernel, which is a suspicious activity. There are some legitimate usages, basically mostly for memory dumps purposes, but this is definitely suspicious and not, it doesn't happen really often. Okay, so we've seen the attack flow of kernel rootkits. We started from kernel loading. We've seen how we can capture a fileless kernel module, and we're able to detect that the kernel module was loaded. We then seen how kernel modules are able to hide themselves and how we can detect it. We've seen how 2 or 3 ways that kernel rootkits are able to place hooks upon the system to be able to see, to modify the response and hide artifacts. And we see some examples for the communication channel and for command execution by kernel rootkits. So this is the kernel rootkit attack flow. And now we get to our last part, which is the eBPF rootkit. eBPF rootkits are the newest type of rootkit, which really surged up in the last year. And we see some examples for them in the internet. And we're gonna see how we were able to analyze some of them and find a similar pattern to what we found in the kernel module rootkit. So this is our original kernel module, and this is what we found after we investigated some of the eBPF rootkits. So basically, overall, it's the same. BPF program loading, after that probe placement and eBPF program hiding. Then you have a communication channel to give a command and the payload trigger. We're gonna dive into all of those and see how each stage is performed. So first of all, loading. We're going back into the eBPF architecture, and when you want to load a new BPF program, you need to load the BPF bytecode into the system. You're doing that by the BPF syscall. The BPF syscall then loads it into the sandbox, and the program is being loaded. What we did is we attached ourselves on that function, on the BPF syscall, and we're able to capture the bytecode before saving it to disk for later investigation. So here we're gonna see a demo. Hopefully, we'll be able to see what's happening. We created a new event named eBPF attach, and we're stating -c BPF in order to see that, in order to capture BPF's bytecode. And here you can see the results. We loaded an eBPF rootkit, and you can see that we have all the information about the rootkit. We're gonna dive deeper into that later. But what's important is we're gonna see below, in the screen below, I'll zoom out in a second, that we were able to capture the bytecode itself, and we're gonna prove that it's really the bytecode. So I don't know if you can see, but we have our path that Tracy is saving the bytecode, and we've written a simple Go program in order to disassemble this bytecode, and we can see that this is really a bytecode, and it uses the right user helper, which is also stated up here, so we can see it's the same one. Okay, so we've seen how we can load it. Now we're going to place some probes. This is the most important part of the eBPF rootkit. As Idan mentioned on eBPF of kernel rootkits, this is where the magic happens. This is where the rootkit technique is really coming to play. So what we did is when we investigated the eBPF rootkits, we found that eBPF rootkits are able to modify or change responses by using several helpers, and we just went over those helpers, and we found all of the lists that are able of helpers that are able to modify the user space. So the first one and the most important one is the BPF probe write user. This allows an eBPF rootkit to modify user space memory. And basically, if you're placing a probe on the return function of a syscall, you're able to change the response. So here we have an example of bad BPF by path to file, which is an amazing POC that does just that. Is placing itself on the return function of the exit of the read function, and it's modifying the return value of the read command. Meaning, if you read the file, it can just modify the content that you get when you're getting that back in the user space. So this is the first and most common one. The next one is the override return helper, which enables you to fake a successful or an error of a function. And this enables you to trick the user or trick a program to think that you're unable, for example, to open a file, meaning that it's not existing or something like that, when in fact it's existing. The next one is SKB stored bytes and SKB pull data. Those two are able to modify communication or data of packets. That allows you to either exfiltrate data from the system to a remote host, or just overall damage the integrity of the data that's going through. And the last but not least, the send signal. This is what attackers are able to do in order to kill a process which is doing something that they don't want to do. For example, if they want to run ls mode to see which kernel modules are loaded, or ls or something of this kind, they can just kill the process altogether, and the user won't get a response. This is also related to the last part, and we're going to see it in a second. So we understood that helpers is the meaningful part of this attack, and we thought to ourselves, okay, how can we find which helpers are being used? And once we ran some of the eBPF rootkits, we found an interesting message in the D message indicating us that a certain eBPF program is using a helper that can corrupt user data, which is interesting. We thought to ourselves, okay, there's got to be a function or a point where the verifier verifies helpers. And exactly that's what happens. So we have our BPF attach function, as we stated before, and you are able to see that we are extracting all of the helpers that are used in the attack, including the probe write user, which is able to see that it's suspicious or even malicious. We're also able to see which symbol this program was attached to, so we know what they're trying to do. For example, in this example, they are probably trying to modify the execve return value. Okay, so we are getting to the program hiding. Now do we have hooking techniques in eBPF? We can modify response. We want to hide our eBPF. And one way to do it is just hook ourselves on the BPF syscall, which we mentioned earlier. So the BPF syscall is used also not only to load programs, but also to list the loaded programs. So that depends on the CMD or the command that is being provided to the syscall. And as you can see in the example, we have an example of eBPF kit by Gilom from Datadog, amazing tool, which is, what he did here is he attached a probe to the BPF syscall, and in certain cases where a listing is performed, he just modified the response, the buffer, and the return value to be able to skip its BPF program. And then when you list the BPF programs that are loaded, you won't be able to see it. Our last step is the communication, which can be either used by maps, which we mentioned earlier, to communicate with user space, or by probe itself. You can just probe on any function in the kernel or user space and just see that the request went through. The payload trigger is the last one, and it's the helper that is used here is the return modifier return value, which can be used in order to kill processes or send them other signals to disrupt their action. So we've seen a BPF program loaded, how we placed hooks or probes on different functions, how we performed hiding, and how we communicate with our malware. And at the end, we'll see also an example for BPF payload trigger in order to kill a process. So let's do a quick recap of our session. First, we saw the user space, most common one, most common rootkit, LD preload, and the less privileged one. Then we saw the most privileged one, which is kernel module, which offer a lot of options and capabilities. And at the end, we've seen the newest type of eBPF rootkits, which is emerging. So what can you do to protect yourself from those threats? Well, you can either monitor, block, or disable features to reduce your chances of being attacked. And you can do it by several means. We've given some examples here. We attached our command line to Tracy if you want to use it. All of the demos that we've seen today are in there, and also we have in our open source behavioral signatures for all of those. There are other tools that are able to detect some of the events. I don't know if they can detect everything. You can block loading of new eBPF rootkits by using eBPF kit monitor by Gilom itself, which wrote the eBPF rootkit malware to block all loading of new eBPF programs. And you can use the kernel lockdown syscall in order to disable modification of the kernel, which can help you avoid some of the hooking placements which are based on modification of kernel memory. So as a parting note, we are inviting you to join us in our research and to be part of the community, ask for any features, ask questions. Our link is over there in GitHub. You're more than welcome to check us out. And as I said, we have behavioral rules available for the detection of all of those things. And if you're more interested on the other side of cloud native research or on CI/CD and vulnerabilities, tomorrow there's also a talk by Yakir and Eli about exploiting vulnerabilities in the supply chain. You're more than welcome to come to here. And if you want to buy us a beer and talk about rootkits, we're all for it. Thank you.
Thanks.
Any questions?
Yeah, so first of all, thank you for a great session. A lot of scary examples, scary pictures. My question about eBPF and compatibility with different kernels. How do you dealing with this mess? Probably you release your containers in a separate builds, Ubuntu, blah, 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 or how? What's your approach on this?
Okay, so we sort of solved it in Tracy. There's something called the BTF, which was introduced in one of the newest kernels.
5.4.
Yeah, which enables you to load eBPF programs without the need of kernel headers, which is great. And for older kernels where we are not, there's no BTF, we have the BTF hub, which enables us to, we just compose the BTF of all of the common distribution, and we're able to load Tracy on almost any kernel and any distribution. And if you have an issue with something specific or custom build, you can just open an issue in Tracy and we'll edit.
Yeah, and you can also use it in your own, like if you're writing your own eBPF tool, you can use BTF hub.
Yeah, it's an open source.
It's open source.
It's also open source project.
Yeah. Thanks.
Thank you for your presentation. It was really great. I have a question about different tools for eBPF. There are a lot of different tools, for example, Falco, BPFTrace, BCC, and other. I remember correctly, Falco, for example, also includes some rules and some additional functions. But what difference between your solution and such as Falco, BPFTrace, and other?
Well, it's a tough question because open source projects are, due to their nature, are exposed to all the other open source developers. So we've seen a lot of common code in other projects as well after we introduced a new feature or something like that. I think that some of the examples can be the content, the rules themselves. Falco has their own rule set. We have our own rule set. I believe that we attack the topic of kernel and eBPF rootkits. I don't know if they have a solution for that, but that's I think we did it before them. And also we started the eBPF, the BPF hub, what we just mentioned, to allow for eBPF programs to be loaded to any kernel. So there are some things that are different. I don't know if they're also allowing the artifact capturing,
Yeah.
but there are some differences.
Yeah, I'll share my perspective. So I think what's different, at least from my perspective, is we build it as researchers and we are continuously evolving it from seeing attacks. So most of what we're doing is looking at real attacks, learning and understanding how we can make this tool better.
Yeah.
So this was part of it. And as Eitani said, I think the artifact capturing is something that I didn't see in many other tools. We can capture network packets, and we can do them by based on every process. So you can get like a TCP dump for every process in the system. So if there is a malware, you will be able to capture that. We are capturing every kernel module that is being loaded into the system, every ELF buffer that is written into disk. We are capturing every eBPF program that is being loaded. So we are really focusing on the forensics side of things and not only like normal observability.
Okay, thank you. And that I have some additional question. I would like to ask about footprint. What about memory usage, CPU usage?
Yeah, so this is something that we put a great emphasis in the last year, mainly to the usage of our open source in the commercial product as well. And we were able to reduce the memory consumption and the CPU consumption to single-digit CPU usage. The last I don't wanna say out of top of my head because I don't remember. I don't wanna promise, but it was definitely single-digit. We gave great emphasis on the performance of the servers.
Okay, and finally, my question about what do you think it's right approach if for example, if you use some machine learning, some sequence to sequence model or other model for analyze sequence of syscall, or maybe rules it's enough for detect all rootkits. What do you think?
So we haven't explored AI in this term yet. We're thinking about it to see, because we have a lot of data from the machine and we're able to see all that happens in the system. I would, for example, with the call user mode helper, probably that would provide, AI would probably detect that. But I think that I'm connected with what Dan said about we're investigating real-life attacks, and each new attack and each new technique that's happening, we're creating a custom-made event for that technique, or using an existing event and adding information to it, so we will be able to see this attack as well. So I think in that term, we're adding information that wasn't there. So AI probably wouldn't have known the difference between a legitimate operation and a malicious one.
Okay, if you imagine, for example, situation, we have some machine learning model, for example, based on autoencoder architecture, and this model looking for some time, all captures all sequence of these calls and learn some normal behavior, yeah. And after that, for example, if we will have some zero-day rootkits on something like this, maybe in this case we can detect some anomaly or not. What do you think about this
I
approach?
think it's possible, but it's really tough to create a model of, from my opinion, for a normal execution of a server, because in the cloud we have so many different products and many servers and kernel
But
versions.
we can learn the personal model for each endpoint. It's not problem, for example.
I think we can definitely talk later after
Okay,
the talk.
okay, thank you.
We have
I think,
some
yeah,
ideas, but I think it's a complex question.
Yeah, thank you
Maybe
very
one
much.
last one, because I saw
Yeah, somebody
someone
else
else
wants?
wanted. Okay, thank you.
Yes?
Come to us. Yeah, sure.
Yeah, thank you very much for the
Thank you.
informative session.
Thank you.
Unfortunately, the session time is out.